We learned a lot about limits in the very first unit of calculus. Every once in a while, we came across problems that had indeterminate form. Indeterminate form was when we had something like 0 over 0, or infinity over infinity, or negative infinity over infinity. And there's a few more that we never touched upon that we'll talk about on the second page of 8.7 today. We're going to learn a rule called L'Hopital's rule. It is French. That's a French guy's name. It's like the rule of Hopital. We're going to learn a rule that helps us evaluate limits that had indeterminate form when you plug in your number. Now, you guys are really going to love this on some problems because you will get to use this instead of doing the factoring and canceling thing, or instead of dealing with those square roots and multiplying top and bottom times the conjugate of that square root thing. Yeah, that whole mess. We're not going to have to deal with it because we have L'Hopital's rule. So, yay! I'm going to be very, very happy about that. Let's review how to take a limit and what to do about like plugging in and everything. In this problem, if you plug in 0 for x here and here, on the top you get e to the 2 times 0. E to the 2 times 0. 2 times 0 is just 0. Minus that 1. Over e to the 0 minus 1 again. So the top is, well, anything to the 0 power is 1. So this is 1 minus 1 over 1 minus 1. So this is 0 over 0. When you get 0 over 0, that is called indeterminate form, and you have to do some other method of simplifying the fraction before you can move on and do anything else. So what we're going to do is we're going to use an exponent property that you learned back in algebra, like early algebra, except we're going to do it with e to the whatever power, so it's going to be a little bit weird. This limit, as x approaches 0, equals this new limit. Okay, our denominator is e to the x minus 1. We're just going to copy that. But the top is the same thing as e to the x squared, right? Multiplying exponents is the same thing as an exponent with another exponent on it. So that was the power property of exponents. Since this e to the x squared is a perfect square, and this minus 1 is also a perfect square, what we have here is the difference of squares. So that factors into e to the x minus 1 times e to the x plus 1. Okay, it's kind of like doing x squared minus 9 equals x plus 3 times x minus 3. It's that same kind of a deal, but it's e to the x instead of that x. All right. E to the x minus 1 and e to the x minus 1, boom, cancel each other out. And we're left with the limit as x approaches 0 of e to the x plus 1. Now we can plug in 0. And since we're plugging in 0, all the x's disappear, which means our limit can go away. So this equals e to the 0 plus 1. Anything to the 0 power is 1, so this is 1 plus 1, which equals 2. So if we graphed out our function, which was that original fraction, if we graph that out, as x gets really, really close to 0, the y values get really, really close to 2. All right, so that was the method that we did early in the year. And I don't have to remind you how terrible it was because we just got to do all that factoring and canceling, and that was kind of annoying, right? We don't want to have to factor and cancel. We want to be able to do a different method that is easier to do, especially now that we know how to take the derivative of e to the x. So e to the 2x is going to be a piece of cake. We know how to take that derivative. Also, sometimes some limits won't factor in a way where you can just cancel out a couple of factors. Or sometimes you have those square root functions and they're just super annoying. Okay, so let's consider this limit. If we try and plug in 0 on top and bottom, we get the same kind of deal as before, where we would get 0 over 0, right? That top is the same as this top. So the top is 0, and then plug in 0 on the bottom, 0 over 0, blah. If we try and factor the top, we get e to the x minus 1 times e to the x plus 1. Neither of those will cancel out with a denominator of x. So there's nothing that we can really do if we get 0 over 0 indeterminate form. So we're going to use L'Hopital's rule. L'Hopital's rule says that if we have the limit as x approaches c is a number, of a fraction. Okay, so for this fraction, f of x represents whatever's on the top, and g of x represents whatever's on the bottom. Okay, so in this one, f of x would be e to the 2x minus 1, and g of x would be x. So it's just whatever's on the top, whatever's on the bottom. So f and g are functions. Those functions have to be differentiable. So you have to be able to take the derivative on an open interval containing c. So you have to be able to take the derivative close to whatever the value of c is, like what you're getting close to right there. That means that your functions f and g have to be continuous, like really close to c, and there can't be like weird stuff going on, okay, making it non-differentiable, so vertical asymptotes and like weird stuff. All right, you don't necessarily have to be able to take the derivative at c. That was a property about limits that we learned like way back when. Don't have to be differentiable at c. Doesn't even have to be continuous at c. Remember limits, like if the left and the right got really close to the same y value, even if there was a hole, the limit equals that y value, you're totally good there. Okay, so we don't even care if there's a point up here or not. As long as the left side and the right side get really close to the same y value, your limit's golden. You're good. We got some more stuff. Assume that g prime of x does not equal 0. All right, so if you take the derivative of this bottom function, you just can't get 0. Okay, so that means that your denominator cannot be a constant. And if it was a constant, you wouldn't get 0 over 0 or infinity over infinity anyway. All right. If the limit of f of x over g of x produces an indeterminate form, so when you plug in c into the top function and the bottom function, you either get 0 over 0 or infinity over infinity or one of the other examples on the second sheet of paper, then you can rewrite the limit, still taking the limit to the same letter, same number. But on the top, you can take the derivative, and on the bottom, you can take the derivative, and those limits are equal to each other. Okay, so I'm going to say that again. We've got the limit of this fraction. If you take the derivative of the top and take the derivative of the bottom, the new limit equals the old limit. Both of those y values are going to end up being the same thing after you plug in the x value. That is so awesome, because it means that instead of having to factor this on the top and then try and cancel, and like who would think about factoring out that being like a perfect square minus a perfect square? Okay, it doesn't look super obvious. Instead of trying to do the factor cancel thing, you can take the derivative of the top function and take the derivative of the bottom function and rewrite it in a new limit and then plug in 0. Let's see how that works. So we've got the limit as x approaches 0 of e to the 2x minus 1 over x. We're going to get the indeterminate form 0 over 0. You have to show that you get 0 over 0 when you plug in. So let's try it. So the limit, x approaches 0. We're going to plug in 0. E to the 2 times 0 minus 1 over 0. So e to the 0 is 1 minus 1 over 0. This equals 1 minus 1 is 0 over 0. 0. Think about that 1. All right. So we get 0 over 0. That's bad. That's indeterminate form. So we get to go all the way back to here and put a slash through it. right? Because limits cannot equal the indeterminate fraction thing. It doesn't equal it because 0 over 0 doesn't mean anything. What this limit does equal, though, is a different limit. Keep the same x approaches 0, keep the fraction bar. And we are now going to use L'Hopital's rule. I'm going to write LH over my equal sign to show that that is the step that I am doing. I'm using L'Hopital's rule, LH for L'Hopital. I'm going to take the derivative of the top and the derivative of the bottom. So first off, what is the derivative of e to the 2x? That's going to be like our e to the u thing. U is 2x. So the derivative is going to be e to the 2x times u prime, which is just 2. We'll put the 2 in the front because that looks a little nicer than in the back. Derivative of -1 is 0. So plus 0, we don't have to write that. On the bottom, you have to show that you are taking the derivative of the x. Don't just ignore it. Put the 1 on the bottom. Derivative of x is 1. We're not ignoring it because you want to show that you know that the derivative of x is 1 and that you have to do that for L'Hopital's rule. All right. After that, you can get rid of that 1, and you can do that now if you want in a rewrite. So limit x approaches 0 of 2e to the 2x. All right, let's plug in 0 now. Equals. If you're plugging in the number for x, you no longer write limit. So this is 2e to the 2 times 0. 2 times 0 is 0. So this is 2e to the 0 power. Anything to the 0 power is 1. So this is 2 times 1. And 2 times 1 is 2. Right? So as x gets close to 0, the graph of this fraction would get close to the y value of 2. So both sides of this fraction graph get close to the point 0, 2. Let's do another indeterminate form. This time we are getting infinity over infinity. Let's try it. Plug in x approaches infinity. Plug in an infinity here in your mind. Natural log of infinity. So this would be right end behavior of the natural log of x. What does that graph look like of the natural log of x? Well, let's review. Natural log of x looks like this. So as we go to the right side, that arrow is always pointing up a little bit. So that is infinity. So this equals infinity over, if you just plug in infinity down there, it's infinity. Or if you look at y equals x, the right end behavior is positive infinity. Okay. Fractions cannot equal infinity over infinity. That's not a thing. Okay, you can't actually equal the indeterminate form, so you put the slash through it. All right. Let's use L'Hopital's rule to say that the old limit equals the new limit. X still approaches infinity. LH over equal sign to show what our step was, to show that we didn't just make this up. Okay, the top, what is the derivative of natural log of x? 1 over x. Bottom, what's the derivative of x? 1. So again, you have to show that you took the derivative of the numerator and of the denominator. All right, let's do a rewrite. We know we don't have to put divided by 1, really. So this still equals the limit as x approaches infinity of 1 over x. Right? Anything divided by 1 is the original thing. Okay, so we've got the limit as x approaches infinity of 1 over x. If you plug in infinity here, you are taking a number and dividing it by increasingly bigger numbers. So if you plug in a 10 here, you get 1/10. If you plug in 1,000, you get 1/1000th. If you plug in 1,000,000, it's 1/1,000,000th. If you plug in 10 bajillion, it's barely anything. It barely registers. the limit of 1 over x as x goes to infinity is 0. That fraction gets so small that it becomes insignificant. The right end behavior of the graph y equals 1 over x is 0. I'm going to graph that one for you as well. Here is 1 over x. X-axis, so as x goes to positive infinity, there is a horizontal asymptote here. Y goes to 0. There it is. Next page. Applying L'Hopital's rule more than once. So every once in a while, you will use L'Hopital's rule, and then you'll realize that when you plug in the 0 or infinity or whatever the number is, when you plug it in, it still doesn't work. You get indeterminate form again. That's terrible. But you know, it's not so bad. You get to just use L'Hopital's rule again until eventually something changes. Let's take a look at what's going to change and kind of disappear as we do L'Hopital's rule a couple of times. If we plug in negative infinity, here's what happens. Plug in negative infinity, we get negative infinity squared over e to the negative infinity, right? There's a negative and there's a negative. We got doubles. So this is positive infinity squared. Infinity squared isn't a thing, it's just infinity. Over e to the infinity power, positive, right? Okay, so as as x goes to infinity, right, we go to the right side, as your exponent goes to infinity, e to the infinity is infinity. This arrow right here. So this is infinity over infinity. We know that limits cannot actually equal infinity over infinity, so put your does not equal. And then we're going to put equals a new limit. X still approaches negative infinity. It's going to have a fraction still, but we're going to use the L'Hopital's rule to simplify out our fraction. Okay, numerator, derivative of x squared is 2x. Denominator, derivative of e to the negative x is going to be e to the negative x times, okay, so if it's e to the u, its derivative is e to the u times u prime. The derivative of negative 1x is negative 1, so just stick a negative right there. That's the u prime. Okay, let's try plugging in negative infinity. On the top, we get negative to infinity over bottom. If we plug in negative infinity, we get negative e to the negative infinity. So again, we're going to the right side because it's e to the positive infinity, but now there's a negative, yeah? Go to the right side. It's going up forever. So this is negative 2 times infinity is infinity. Okay, bottom, negative infinity as well. Cannot equal infinity over infinity, cannot equal the indeterminate form. All right, so we got to take a derivative again on top and on the bottom using L'Hopital's rule. We're applying L'Hopital's rule. L'Hopital's rule takes a limit, gives us a limit. It does not give you a value, it gives you a limit. On the top, 2x has a derivative of now just 2, and then the bottom, e to the u times u prime. E to the u is still e to the negative x. U was negative x, its derivative is negative 1 times the negative 1 we had, turns this to a positive e to the negative x. All right, so what has changed? The top really is the thing that's changed. Instead of having x squared, having an x value of any sort on top, that keeps decreasing, so we have fewer and fewer x's on the top until eventually we don't have any x's up there. So as we continue, we plug in negative infinity here for x. This is going to equal 2 over infinity, right? Negative infinity is positive infinity, and e to the positive infinity is this arrow going up, so the y values are going towards positive infinity. Any constant over infinity equals 0. So again, you cannot equal something with infinity, but it equals 0. Next example, indeterminate form of 0 times infinity. This cancels out. This guy makes it as big as possible. Why can you not have this indeterminate form? Here's why. Limit properties say that you can split up two different factors. So the limit of e to the negative x times the limit of the square root of x, as long as both of those limits exist. If a limit goes to infinity, the limit does not exist. So you cannot break this up, because even though the e to the negative x would go to 0, right, that's 1 over e to the x, so would go to 0, the square root of x, if you plug in infinity there, would go to infinity. So that limit would not exist, but this limit would exist. So we got to do some extra math to figure out what the limit actually equals, whether it's 0 or infinity or some other number. Okay, so we're going to rewrite this in a different way. Let's rewrite it as a fraction of this being e to the x in the denominator. So this equals the limit as x goes to infinity of the square root of x over e to the x. Negative to the bottom, square root becomes a 1/2 power. So we just did a rewrite. We did not take a derivative or anything. All right. We know that we would get 0 times infinity cannot equal, or infinity over 0. Again, cannot equal. Let's take the derivatives on top and bottom using L'Hopital's rule. LH. X to the 1/2, the derivative is 1/2 x to the negative 1/2. Bottom, e to the x has the derivative e to the x. How beautiful is that one? Let's do some rewrites. So this still equals the limit as x approaches infinity of e to the x is on the bottom. That looks great where it is. That 2 can get put down on the bottom as well. X to the negative 1/2, negative moves the x to the bottom. The 1/2 puts it in a square root. And then the only thing left on the top is this 1 up here. All right, now let's plug in infinity. We get 1 over 2 times infinity times infinity. So this is 1 over infinity, which is 0 again. Okay, so it does not really equal 1 over infinity because that's not a thing, but it does equal 0. Last example is this indeterminate form. If there is an exponent that is an x, we're going to end up with some kind of weird stuff. You guys are going to have to buckle in on this one. This is kind of an intense problem. Alrighty, so this guy. We are taking the limit as x approaches infinity of something with an x to an x power. Now, if this exponent was like a 2 or a 3 or something, we could do like, if this was a 2, we could FOIL this out. And then we could take the limit as x approaches infinity, and that one would not be so bad. The issue is that this is an x exponent, so we have to do some weird logarithm property stuff in order to take the limit. Okay. So let's start by looking at this bit right here. We want to take the limit as x approaches infinity of all of this, but let's look at y equals 1 plus 1 over x, all of that to the x power. In order to get the x out of the exponent, we can use a log rule. So if we take the log of both sides, natural log of y equals natural log of 1 plus 1 over x to the x power, right? We've done that to both sides, not just one side. We're allowed to do that. Let's rewrite the left side. Natural log of y equals, And we're going to take that x exponent and bring it down in front. X natural log of 1 plus 1 over x. If we think about x going to infinity, this right here would go to infinity. This would go to 0. So natural log of 1 is 0. This would be infinity times 0. This would be that indeterminate form that we just talked about, right? Infinity and natural log of 1 plus 0. So that natural log would have a limit of 0. Infinity times 0 is indeterminate form. So we have to do something to get a fraction out of this. So we're going to do something weird with this x. This is going to be the natural log of 1 plus 1 over x over 1 over x. Right? Divide by 1 over x is the same thing as multiply by x. Flip the fraction over and multiply, right? So this still equals natural log of y. Alrighty. We're going to ignore the left-hand side for the moment and think about the limit of this side. So limit of this. Limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. The top, we talked about how that would go to 0, right? Infinity here, this would be 0. 1 plus 0 is 1, and natural log of 1 is 0. Over. If x is infinity, 1 over x is 0 again. So this is indeterminate form. Since that limit is indeterminate form, we can use L'Hopital's rule to rewrite our limit by taking derivatives of top and bottom. Okay, so the top natural log of u has the derivative of 1 over u times u prime. U is 1 plus 1 over x. Sorry. 1 over u times u prime. So 1 plus 1 over x times the derivative of 1 plus 1 over x. The derivative of 1 over x is negative 1 over x squared. Reminder, 1 over x is the same thing as x to the negative 1, and its derivative would be negative x to the negative 2, which is negative 1 over x squared. Not see that whole thing. There it is. The denominator, 1 over x, its derivative would also be negative 1 over x squared. So you might notice now that this little bit and this little bit are equal to each other. They are both factors, so you can cross them out. Let's keep going. We're going to now take the limit. We're going to plug in infinity right here. So this would be 1 over 1 plus 1 over infinity is 0. So this fraction equals 1 over 1, which is just 1. Okay. So if we take the limit of the right-hand side, that's the same thing as taking the limit of the left-hand side. So this whole left-hand side is still just natural log of y. Natural log of y equals 1, which means e to the 1 equals y. Yay. Which means that the limit as x approaches infinity of y equals e, and y was our original function. Yay. I am never going to give you a problem that is that difficult. We want to use L'Hopital's rule to make medium problems more simple so that you can plug in and get just like a simple number. I'm definitely not going to give you a problem that is this difficult. It's totally possible that going to a university, they might give you a problem this difficult and expect you to be able to do it. I will not. All right. Have fun on the assignment.